Alright, in this video we will continue what we started in the last video dealing with circular motion. We already talked about that one type of way the velocity vector can change is its speed can change. It can speed up or slow down. If you have that, you have what is called tangential acceleration. Another way the velocity vector can change is its direction can change. This is something we didn't have in straight line motion. If you have a curved path, you are guaranteed to always have this type of acceleration. This type of acceleration where the direction changes is known as centripetal or radial acceleration. And centripetal acceleration is due to the change in the direction of the velocity vector. Now centripetal is actually telling us something. It's telling us the direction that this vector points. Centripetal means center seeking. And what this means is that this type of acceleration always points toward the center of a circle. Now you might say, but what if I'm not following a circle? What if I'm following some sort of curved path like this? Well, at any point on there, that path forms part of a circle. And there is a radius of that. And that radius has a name in physics and mathematics. It's called the radius of curvature. So even though you may not think of this path here as a circle, it actually is a series of many circles. And the acceleration, centripetal acceleration, points along the center of that circle. For instance, it would point this way at each point. So at that point right there, if that's the circle that forms the radius curvature, the centripetal acceleration points inward along that radius. Now in this course, mostly at the introductory level, we tend to stick with just dealing mostly with just a plain circle. But in more advanced classes in physics and engineering, that's not true. Things go on and get more complicated, and we deal with paths, for instance, like what I just showed you. So centripetal means center seeking, and it tells you that the centripetal acceleration always points to the center of the circle. Something else that we know that's useful, that's not always pointed out in textbooks, and that is, remember that if this was our little object here, and let's say our object was speeding up, then it's going to have a velocity in this direction. There's v, and if it's speeding up, then it's going to have a tangential acceleration in that direction. And if it's slowing down, its tangential acceleration is going to be in the opposite direction. Regardless of which direction it points, the one thing I can tell you is it's going to be perpendicular, that acceleration, to our red arrow here that represents the centripetal acceleration. So what we really have are the two sides of the triangle, one by the tangential and one by the centripetal. And if we vectorially add them, we get the total acceleration. So we're not talking about x and y components anymore. We're talking about the component due to the curved path, changing the direction, and the component due to the speeding up or slowing down, changing the speed. Still breaking vectors into components. Always breaking vectors into components. All right? But they're different components. They're not based on x and y anymore. So this is a really, really useful fact that I will use in a little bit to find the total acceleration. Always perpendicular to the tangential acceleration is the centripetal acceleration. Now, let me put in some things that I've already said. An object traveling in a curved path must have this type of acceleration. This is going to come back and be important in the later chapter when we talk about Newton's second law, because if you have acceleration, you must have a net external force, we're going to find out. So when later on we're going to do curved problems, don't you tell me if it's on a curve that there's no acceleration, because that'd be wrong. There is always acceleration when an object is not going in a straight line, guaranteed, and it's going to be this type of acceleration. Furthermore, as I talked about a minute ago, not only is it perpendicular to the tangential acceleration, but it's perpendicular to the tangential velocity vector, which means that nothing actually moves in the direction of the centripetal acceleration. Let me show you kind of an interesting thing. Here's the Earth. And let's say we have the moon. And the moon is going around the Earth. And at this point right here, this is the velocity of the moon. But the moon is accelerating. It's got centripetal acceleration, let's call that A sub c, toward the Earth. Oh my God, it's accelerating toward the Earth. It's never going to hit it. I didn't say it was moving toward the Earth. I said it was accelerating toward the Earth. This type of acceleration, is perpendicular to the actual direction the object moves. I'll tell you something even more exciting. The Earth is accelerating toward the sun. I didn't say it's going to hit the sun, but it is accelerating to the sun because it's following a curved path in which the sun's at the center of the circle. So, this is why the moon can be accelerating toward the Earth while not moving toward the Earth. This is a difficult concept not only for students but for people for thousands of years. Acceleration and motion are not the same thing. All right? When you mean something's going toward it, you mean moving. It has a velocity that it doesn't mean the same thing as accelerating. Acceleration, the net acceleration, is in the direction of the force. What our little diagram shows is that there's something called gravity pulling on the moon. Now, in the case of centripetal acceleration, there is a nice formula that you're going to want to know. It only tells you the magnitude, doesn't tell you the direction. The direction, you have to point to the center of the circle. And that's where you get plus and minus signs from. As far as the magnitude, the formula that we will find really useful in the short time is this. The acceleration is equal to the speed squared. Notice I didn't say velocity. I don't know what it means to square a vector that has a direction. Like what's it mean to have north squared? That doesn't make sense. It's the magnitude, the size, the number squared, divided by the radius of the circle. So let me put that in there just so it's in your notes. That's speed. And you're going to square the speed. And this is the radius. Also, there's another formula I put here that looks kind of weird. It has a radius as well. It turns out that it's going to be useful in a later chapter and maybe more useful than the one I'm giving you now. This is the angular speed. That's what this weird looking Greek W is, called omega. Well, it turns out that we're going to talk about spinning angles, and people will tell you something rotates at 30 RPM, 30 revolutions per minute. That is an angular speed. Or it's going 12 radians per second. We'll come back to that later. The advantage of this is that every object on a spinning disk can have the same omega. So the only thing that differs between different points will be r, one thing. But on a case where you deal with these two vectors, every object on, say, the wheel of a car will have a different v and a different r. And so the two things vary, which makes it more confusing. So this is more useful in later parts of the course. But this is the one that we're going to use right now. And it's useful when you deal with just one object, like this object, going around in a circle. It's not so useful when dealing with something like a spinning wheel that has lots of particles on the wheel. All right, you'll want to be able to know this formula. You put it to memory. And if you think, well, you're just making up stuff and now I got to memorize it. No, if you had calculus and you know the basic definitions of polar vectors, you can derive this from the calculus just by knowing the definition of acceleration, that it's the derivative of velocity with respect to time. But because the math skills are not there yet at this point, we generally either have to do it with trigonometry or we just memorize it. So it's a disadvantage, so we have to memorize, but it's very important. We're going to use it a lot, so make sure you put it to memory. Know that formula. We'll use it in lots of problems. And as you get better, you'll be able to derive it on your own. You won't have to memorize it.